Students, today we'll go for the next video. Okay, in the last video we had seen the classification of chromatography. Okay, classification of chromatography, and uh, very distinctly we have classified this chromatography based on the mobile phase, based on the polarity, okay, based on the principles. So like this, okay, so different way and in a very brief way we have classified the chromatography. Today we'll go for the theory of chromatography. So there are two theories. One is plate theory and second is rate theory. Plate and rate. Okay. So this plate theory was first observed by Martin and Singe. Martin and Singe. Okay. So and these worked on this plate theory, and they have given an equation that is HETP is equal to L by N. So what is this HETP? HETP is nothing but height equivalent to theoretical plate. Okay, height equivalent to theoretical plate. So this is what HETP is given by L by N. So what is L? L is nothing but length of the column, and N is number of theoretical plates. Okay, N stands for number of plates. So N is number of theoretical plates. Okay, so this is what about the what about the equation which is given by Martin and Singe. And here one thing is to be noticed, that as the number of theoretical plate increases, the suppression will be very better. That means this is will be less, and when this will be less, the suppression will be better. Okay, this is what we have to keep in the mind. So what is this? This is number of plates, means what, in any column if you take, so as the number of plates is means more, like this. So 1 2 3 4, how many times much times you can take, these are called the plates. Okay, like this. And this is your stationary phase, and this is your mobile phase. Okay, and if you start from this here, so if you take this around solute here and want to you take anything, so you take it for any 40, like this here. And if you want to uh, now extract here, okay, so from the mobile phase here, so what will happen now? So there will be some of the solute will be extracted from the mobile phase here, and you can see that if the theoretical plates, now if we go for next slot here, so what will happen? 1 2 3 4 5, something like that. So it may fall to what here, now some will go here, so 20 will remain and 20 will go to the mobile phase, like this. Okay, so like this. Now what will happen? Now this 20 mobile phase will carry to the next here, like this. Okay, and in the next case what will happen now? So this 20 will be carried here, so 20 will come here, like this, top level. Okay, and this will come here, that is here, like this. Okay, so this is how I can, this is the traveling here, like this. And finally you can see that here from 40, 20 is being separated from 20, then 10 will be separated from 10, 5 will be like this. So like this, slowly what will happen now? The separation takes place, and finally we get a very separation in different this one, like this here. So all differently going less, and we are going to get a different separation here. And here also the increased solute, slowly the solute will be increased, as the mobile phase is going to extract some of the solute, and slowly it is going to be separated here. Okay, so what will happen? Finally the result will be such that, so we are going to get a very better separations, like this, slowly covering all the, like this. Okay, so almost all the plates is covered in this way, separation. So like 7, no, 1 2 3 4 5 6 7, like this. So this is how the separation takes place completely. Okay, but if you make the number of plates less here, so then what will happen? Separation will be like this, it will be here, like this here. That means separation will not be good here. So as you increase the number of plates, the separation you can get is very nice here. So all will be separated and you are going to get a different peaks, okay, like this. Nice separation will be there like this. Separation for A, separation for B, separation for C, like this. So you are going to get nice separation in the form of the peak. But if the number of plates is very less, if you take the number of plates very less, so what will happen? The same three peaks may not be very distinct way, so it may come in somewhat like this, something like this it may come. So you see this and see this, it's not distinct, but these are very distinct ABC. Okay, so this is how we can say that as the number of plates increases, the separation will be very good. Okay, and if you make this number of plates less, separation will be haphazard, separation will not be good, and you can see it will result to such type of peak presentation. But as you go on increasing the number of plates slowly, so you can see here I have shown only few have shown, but that is not necessary. So like this it goes on separating each and everywhere, and you can see a broad spectrum is going to observe if the number of plates is more, and it shows that the separation is eluted. Okay, so elution of the solute is what do you say is better. So this is what it speaks about the uh, plate theory. Okay, so plate n should be greater. If n is greater, then greater will be the suppression technique. So this is what about the plate theory. So next we will go for the rate theory. Okay, so rate theory can be given by the Van Dimter equation. Okay, Van Dimter equation is there for your syllabus, Dimter equation. So what does this say about the rate theory? So it is given by this equation that HETP is equal to A plus B by mu plus C mu. Remember this. Okay, this is a Van Dimter equations where HETP is equal to A plus B by mu plus C mu. Very important. Okay, this will be asked many times. So this also is called Van Dimter equation. Okay, Van Dimter equation. So where you can see here, you know that what is this HETP. So HETP is nothing but your height equivalent to theoretical plate. This we know, height equivalent to theoretical plate. This is new one. What is A? A is nothing but Eddy's diffusion. A is this is new one. They will ask for 2 marks. Eddy's diffusion. A is nothing but Eddy's diffusion. Okay, and B is longitudinal diffusion. B is nothing but longitudinal diffusion. Longitudinal diffusion. So B is longitudinal diffusion. C is mass transfer rate. Mass transfer rate. Okay, C is mass transfer rate. Mu is flow rate of mobile phase. Flow rate of mobile phase. Flow rate of mobile phase. So like this, the Dimter equation is given by this in the rate theory, where HTTP is nothing but A, Eddy's diffusion, B, longitudinal diffusion, mu, mass transfer rate, okay, and C is nothing but mass transfer rate, and mu is flow rate of the mobile phase. So like this. So this is how it's called as the it's explained by the rate theory. What is this Eddy's diffusion? So 2 marks, or like this they may ask you 2 marks, or elaborate this they may ask you. So what is this Eddy's diffusion? See, Eddy's diffusion is depends on the movement of the solid molecule. For example, if you take this column here, and if you feed up this stationary phase like this, okay, which are in haphazard way like this. Okay, so this is a stationary phase, and if you want to separate the substance now here, 1 2 3, so what will happen now? Eddy's diffusion, what it says that they may take a different path, or that's why it is also called as multi-path effect. This is also called as Eddy's multi-path effect. Okay, multi-path effect. What will happen now? 3 may take this path like this, very simple path it may take to come out like this, and it get elute first. It may get elute first. Now what B solute may do, so it may not take the path like 3, it may go a little bit more like this, like this, like this, like this, see, and then get elute. So that means the second elute we can't say, but I'm taking here second now, since it is taking little bit more root, more root than third one, so it may get a second diluted. Now what is first may take again a bigger root now, like this, 1, like this, 2, 3, 4, 5, 6, then 7, then 8, then 9, like this. So like this, so third. So what happens now here, C may get eluted last. Why? Because it has taken a long route here, like this, like this, like this, like the coming here, like this. So this is what. So these all things will result, in a broadening of the spectrum now. Okay, so what will happen now? So they are going to get a broad spectra. So Eddy's effect will lead to the peak, broadening of the peak here. Okay, why? Because you can see that all these three solutes may not go in a single path. Okay, so they have their own path to elute themselves from this column, and that effect we call it as a Eddy's effect. Okay, so this thing you have to keep in the mind, but this Eddy's effect is not observed in gas chromatography. Okay, in gas chromatography we don't see this because the mobile phase is gas, because the mobile phase is gas here, and that's why here the capillary column is used. Okay, the capillary column of particular nature is used here. By which you can see that this Eddy's diffusion or path different multipath method is not been seen here, so it is very negligible, and that's why the HETP, okay, for the gas chromatography becomes to be B by mu, okay, plus C mu. So A is not there, so Eddy's diffusion is not shown in the gas chromatography because A is negligible. Okay, A is negligible in gas chromatography. That's why the formula for gas chromatography becomes HETP rate formula, which is equal to B by mu plus C mu. B by mu plus C mu. So this is what about the Eddy's diffusion. Now coming to the next, that is longitudinal diffusion. Longitudinal diffusion, that is your B. Okay, what is this longitudinal diffusion? So it also depends on the movement. So this column, if you take this, okay, solute like this, they are in a one particular you can say placed here. So when you go for the mobile phase like this, running of the mobile phase, what will happen? Now they may travel along with this, like this, like this, here one, like this, here. That means they are not traveling in a particular fashion. So in one way, so there will be concentration will be more, in some concentration will be less. Is it right? So there will be turbulence type of nature here. Okay, so turbulence, you know, no, so that's not exactly here. So some may have the higher concentration, some may have the lower concentration, something like that. So it's not in a proper way here, and that also may lead to sometimes the broadening of the peak. But if you see this longitudinal, so in column chromatography, it is B is negligible, like in gas we have seen. So here in column chromatography, B is negligible because in column chromatography we are using liquid as a mobile phase. Liquid as a mobile phase, that will have very less effect on this longitudinal effect, and that's why in column chromatography now it becomes HTTPs will be become, that is A plus C mu. So this is what. Okay, so here B is negligible because B is negligible. B is negligible. So this is what about the column chromatography, and Dimter equation will shift to in this way. Okay, A plus C mu. So B will not be there, and you can see that peak bonding also will be affected here because of the longitudinal diffusion, because of the turbulence shown, effect shown by the movement of the mobile phase. Okay, so this is what about this. Now the last this one remained is here, that is your mass transfer. Okay, so this is what here, mass transfer rate. Mass transfer rate, what is this? This depends on the affinity. Again here, this depends on the affinity of stationary phase or mobile phase. Affinity of stationary phase or mobile phase towards analyte, towards the analyte, or the you are interested solute to be separated. So this is what about the mass transfer rate. If you see again in the column, and if you put a stationary phase here like this, okay, you are putting a stationary phase, this is a stationary phase, and you see that sample to be separated, so is here like this, this is sample to be separated like this. Okay, now what will happen if you put a mobile phase here? So this is a mobile phase. So what will happen now, if the sample is having much affinity for the mobile phase, what will happen, this mobile phase will move along with much of the, what is that, your sample, like this is called mass transfer. Okay, and if your sample is affinity to the adsorbent here, so what will happen, the mobile phase while moving, it may not take much of the solid, it may take very less, so mass transfer is low here. So like this, depending on the affinity of this, we can see that the transfer takes place. So this also is same thing here. So there is no normal transfer here, so it depends on the affinity nature. And this also leads to the some difference in the peak, of getting the sharp peak here. Okay, so this is what about the mass transfer. And finally mu, so mu is nothing but flow rate of the mobile phase. And usually fast the flow rate of the mobile phase if we keep, good is a suppression, but it should be optimum, it should be optimum. Okay, so if you keep too high mobile phase flow rate, then what will happen, it will take all the solute along with it, and the suppression will be nil. Okay, this is a condition. And if you take too slow mobile phase, then definitely there will be again the mobile phase will take much time, spend much time with the sample or the stationary phase, and again there will be weak suppression. That's why optimum flow rate should be there, we say optimum. Okay, exactly what we require, exactly, not too high, not too slow. So main optimum is near to the high only, but not too high, near to high. So is very good flow rate for the better suppression. Okay, so this is how the theories of chromatography in this video we learned. Okay, so very important. So they may ask for 2 marks, 3 marks, the theory of chromatography, that is your rate theory, which explains the Dimpter effect, Van Dimpter equation. Okay, and the plate theory, so where we could see the equation of HETP is equal to L by N. So like this. Okay, hope you understood this video of theories of chromatography. In the next video we'll go with the next complex. Thank you.